In this video, we will talk about Chapter 10, Sections 1 and 2, Plate and Frame Heat Exchangers.
The plate and frame heat exchanger was invented by Dr. Richard Seligman in 1923, but their use became much more popular in the 1930s. It is a type of heat exchanger that makes use of several metal corrugated plate sheets that are clamped together to transfer heat between two fluids. The advantage of this over a conventional heat exchanger is that the fluids are in contact with the larger surface area of the plates. This allows for a much greater transfer of heat, therefore increasing the rate of the fluid's change in temperature. Different patterns are used in the plates, such as the washboard and the herringbone pattern. In the herringbone pattern, the angle made between the adjacent ribs and the vertical ribs are called the chevron angle, theta. Plates can be made with small chevron angles, low theta plates, or large angles, high theta plates. Performance of the heat exchanger is a function of the chevron angle. High theta plates are able to provide higher heat transfer rates with high pressure losses, and the opposite is true for low theta plates.
Plate and frame heat exchangers are constructed from metal plate frames and gaskets that separate the fluids. These heat exchangers can be used for either countercurrent or parallel flow designs. The surface of the plate in the heat exchanger is very important to the transfer of heat because it is the area in which heat is conducted. The plates within the heat exchanger are corrugated. This imparts stiffness to the plates when they are clamped together. The corrugating of the plate surface also allows the fluid mixture to become turbulent, enhancing the transfer of heat. The construction of plate heat exchangers requires very little to no welding. They are often shaped through cold forming and clamped together with long bolts and nuts. This simple construction allows for easy disassembly and maintenance. The most common material used in its construction is stainless steel AISI 304. Titanium is also used for its resistance to corrosion in systems containing chloride or brackish cooling water. Other materials used include nickel, zirconium, or brass alloys, as well as pure metals like copper, silver, or aluminum. The gaskets of the plate heat exchanger are used to separate the fluids. These are usually constructed of materials such as natural rubber, styrene, silicone, or butyl rubber. The construction's maximum pressure is limited by the strength of the material's frame, while its operating temperature is determined by the strength of the gasket's material.
The purpose of a plate and frame heat exchanger, much like any other heat exchangers, is to transfer heat from one matter to another. In this schematic, we will initially take note of the cold fluid. For sake of simplicity, the initial few plates is shown to be widely separated in an exaggerated way so that the flow of the fluid can be demonstrated better. The blue color represents that the fluid is cold. After it passes through the inlet, the fluid is allowed to spread over each of the even-numbered plates as shown in the figure, and the direction of the flow along the plate is upward. Now the second figure shows that the warmer fluid, represented by the red color, enters the other inlet and is allowed to spread over the odd-numbered plates only, with a direction that is downward. And because of the opposite direction of the flow of the two fluids, this makes it a counterflow heat exchanger. Now in the next figure, let's consider that both of the warmer and the cold fluids entered their respective inlets. The two fluids pass through the plates alternatively and therefore exchanges heat in the process. Now let's take a look at a single plate in the heat exchanger. Here we can observe that the heat is transferred through the plate from the warmer fluid, which is on the left hand side, to the colder fluid on the other side of the plate. There will be a conduction resistance due to the plate and convection resistance because of the two fluids. The combined thermal resistance is equal to the sum of the resistance due to the conduction and convection, and multiplying this combined resistance with the surface area of the plate will help define the overall heat transfer coefficient as shown by the equation.
Convection coefficient and pressure drop. The hydraulic diameter for a rectangle flow section is dH equal to 4SB by 2S plus 2B, where S is the distance between the plates and B is the width gasket to gasket. The port loss is calculated as a loss coefficient multiplied by kinetic energy of the flow in port, inlet, or outlet itself. Delta P port is equal to 1.3 PV P squared by 2, where Vp is the velocity in the port, the total measured loss associated with the flow, and either streamed through the exchanger, then it is sum of the delta P plates and delta P port.
Plate and heat exchangers have large conductance coefficients, up to 6,000 watt per meter squared Kelvin, for liquid-to-liquid use. They are ideally suited for low viscosity fluids. The projected area of plates is usually taken as nominal heat transfer area, in spite of the real curved surfaces and loss space in gaskets and ports. The major limitations in plate and heat exchanger are maximum allowed pressure, usually below 1 megapascal, and the temperature range, which is usually limited to 150 degrees Celsius. To solve for the heat transfer, the log mean temperature difference can be used if the flows are either entirely counterflow or parallel flow. However, a correction factor is calculated to solve for the log mean temperature difference. The correction factor is indicative of how efficient the exchanger is thermally. To solve for the correction factor, we must first solve for the number of transfer units using the equation shown here. Then plug in the value for n and solve for the correction factor. If the flow through the exchanger is entirely counterflow or parallel flow, then delta T would be the log mean temperature difference. Delta T can be solved by multiplying the correction factor with the log mean temperature difference of the counterflow or the parallel flow. Finally, we can solve for the heat transfer within a plate and frame heat exchanger.
The fouling factor is added to the overall heat transfer coefficient in order to compensate for the fouling that occurs on pipes or other surface areas. It is the buildup or accumulation of stuff, such as calcium or rust, that may occur naturally over time. Why is fouling a bad thing? Fouling on a surface is considered a resistance. Now, heat must transfer through this additional resistance, and depending on the application, we may not want that. So how can fouling be prevented? Routine maintenance, such as cleaning or replacement of old parts, such as pipes, will help reduce the fouling that is occurring in the system. Certain designs, such as plate and frame heat exchangers, may also be implemented. These heat exchangers have smaller fouling factors than other heat exchangers. This is because these heat exchangers have smoother surface areas to keep the deposit of minerals and other solids from forming. These heat exchangers also keep a high degree of turbulence in the flow, keeping the solids in suspension and thus further reducing fouling on the pipe.
In conclusion, plate exchangers are well suited for liquid-liquid flows under turbulent conditions. These exchangers can also be used as condensing units operating at moderate flow rates and pressures up to 60 psi. The performance of a plate and frame heat exchanger is a function of the chevron angle, which is the angle made between adjacent ribs and the vertical for a herringbone pattern plate. The maximum allowable pressure of the fluids is determined by frame strength, plate deformation limits, or gasket retainment ability. Frame strength is usually the limiting parameter for the maximum allowable pressure. Operating temperatures are usually limited by gasket strength or tendency to decompose. To review, the main advantages of plate and frame heat exchangers over other heat exchangers include the following. They have smaller fouling factors due to the reasons discussed previously. They are simple to clean, and chemical cleaning methods are rapid and highly effective. Mechanical cleaning is easily performed because they can readily be taken apart. They are small in size and can be modified readily. If an existing exchanger cannot transfer the required amount of heat, for example, one or more plates can easily be added as needed.